Hey everybody, welcome back to a rather special edition of HPC Tech Shorts. This week, and this time, I'm joined by Olly Perks. Hey Olly.
Hey Booth, thanks for having me on this week.
Olly is a principal engineer in the HPC engineering group at ARM, and so together we've both been involved in supporting the ARM HPC user group to run a summer hackathon, which is coming up in about a month. Now we're doing this because when we look across the HPC space at a lot of the hundreds of HPC codes that are out there, in fact there's thousands of HPC codes. We obviously both want to see them work really, really well on ARM-based CPUs. AWS has got the AWS Graviton that we've built using ARM recipes, and we want to see the HPC community fully enabled across all of the ARM-based life forms in the world. So now the other goal of the hackathon is to let everybody out in the HPC community have a bit of a play with some new things, and ARM is a pretty new thing in HPC to a great degree. We've seen some great results recently with Wharf and GROMACS and a bunch of other codes running on our AWS Graviton based machines, our C6GNs. But we want to just open the doors and let everybody come in and have a tinker with all of this stuff. Now to do that, we're going to make a whole load of HPC clusters available during the week of the hackathon. Like I say, with Graviton 2s in them, lots of EFA enabled machines as well. So all of them will have access to our, super fast HPC fabric, that you can, you just access through MPI. And I think we're going to get into all of the details of that in a minute, Olly.
Yeah, absolutely.
We're also going to have live talks from experts throughout the week, folks from ARM, folks from AWS, folks from other groups like Spack and reFrame. And so anybody who joins the hackathon that we're supporting AHUG to do is going to get access to a whole flotilla of different tools and have quite a lot of fun during the week, at least we hope. So we're really hoping to see a lot of folks out there jump in. Even if you don't want to compete, we are going to be, AHUG's going to award an Apple M1 MacBook to each member of the team that moves the needle the most in terms of their contributions in the comp. But even if you don't want to compete, even if you just want to turn up and have a tinker, have a play and observe, you're more than welcome. So the details, I'm just going to put the banner up now with here's the registration details. You'll find the registration and a bunch of information about the event are here. Let me just, this is where we are at the moment. It is, of course, a GitHub page where we've put all of this information. But you'll find a lot of background of the competition and the event there. Now, it's been a while since we've had a new CPU enter the HPC world. And I think we've all got a little rusty over the years and started to make a lot of assumptions about, the build target is always x86. We know that we need to get into the build tools and the build systems, get software actually building and working well on ARM so that we can get it performing well on ARM. This is going to be a long-term mission for all of us in the HPC community. In that time, since the last major CPU earthquake in the HPC community, things like Spack have come along, right? New tools.
Absolutely. And Spack's been an absolute revelation for us in terms of how we can manage software dependencies. I mean, HPC is almost self-defined by its complexity. And so installing applications just isn't trivial. And so having dedicated tools that manage dependency chains, variations is just so useful for anyone trying to keep track of the software installed on their system. And it's really growing in momentum. So it's not only a great choice for this workshop, but something that I would really encourage people to be using after the event to properly manage software in HPC environments.
We're also going to be using reFrame as well, which is another tool that is useful for doing regression tests for an application. And we're going to use that how are we going to use that, Olly?
Yeah, so again, reFrame's super interesting and it's kind of new to us. So we've been learning on the job as well. But it really allows you to track the job submission and performance and validation regression of test cases for HPC applications. So this is a really important topic to be checking, not only that your code isn't getting slower with subsequent changes, but also that you're actually getting the right answer.
Yeah, correct.
And we all know that kind of validation tests in HPC really aren't as robust as they need to be. So actually having a common framework that we can put all of these application recipes in and test case recipes in is really going to be useful for us. And actually the team behind that is really excited to have so many potential applications being imported into their system. So
right, and so and the other thing that's happened also in all of that time since the last big CPU earthquake, is we've the cloud has come along, right? And so and the cloud enables, like, we can take the Spack recipes, automatically build them if we like to in a CI/CD pipeline, deploy them into reFrame, so the reFrame goes and does an automatic run of a bunch of scale tests, checks to see if we got the right answer, faster than last time or slower than last time. We can have an automated patrol system if we like, and this is one of the things that AWS wants to contribute into this space. And so if we want to get HPC workloads working uniformly well on ARM, and in fact, kicking butt actually, we really need to put in the telemetry so that we can see where the next level of effort needs to be put. And even if during the hackathon this summer, we find out that a bunch of codes don't work so well on our ARM-based processors and on our systems, that's a data point that tells us where we need to go and plow a bit of extra effort, right?
Absolutely. We don't do this in isolation. So it's really useful to have all of this data to guide where we as a community invest our effort going forwards. So
plus it. That sounds good.
I'm just going to start at exactly where you left off. So we're on the GitHub page for the workshop, and I'm going to grab the address for that, and we'll use that in a second.
Okay.
Right. So I'm just going to jump into my virtual machine. Don't need that anymore. So we've made this big thing about doing this event in the cloud, but actually we're hiding quite a lot of that aspect behind all of the infrastructure and processes. So for most purposes, this is just going to look like any kind of on-prem cluster that you might have access to already. So I'm just going to log in, standard username. I've got an IP address here. All of my SSH keys are already set up, so I should be able to just log straight in. And lo and behold, I'm onto an AWS instance. Now, this is actually our cluster head node. So we can have a look. Right, we've got 2 queues set up. We've got 4 nodes available in each of those queues, and these queues denote the AWS instance types that are available behind them. So we've got a queue for C6G nodes, which is the Graviton 2 nodes, and then the C6GN nodes. And this is the Graviton 2, but with the EFA network adapter. So this is giving kind of 4 times the network bandwidth and some latency improvement. So this is the kind of real HPC version for the C6GN.
Yeah. Folks had used the C6G if they were doing a lot of single node runs, where the networking aspect wasn't so important or wasn't important at all.
Absolutely.
And C6GN if you're running like MPI-based lifeforms and you just want everything to happen lickety-split. Yeah.
Exactly. So that's where we really want to be by the end of the workshop. And both of these are backed by 16XL instances. So these are the 64 cores per node. So we've got 256 cores in each of these queues available to us. So this is already quite a big cluster, and this is just our demo one. So I'm logging in. I've got nothing available to me. So the first thing I'm going to do is I'm going to clone this Git repo that we specified. And we can get into here, into the tutorials folder, and I've got an application pre-prepared in here. And this is what we're going to be using for our quick demo today. So obviously we need to actually build our application to run. So we're going to be doing that through Spack. So I can actually have a look at what compilers Spack has available, and it will tell me that, right, we've got 3 compilers available, an ARM21 compiler, and this is the ARM compiler for Linux, a GCC 10.3 compiler available, and an NVHPC 21.2 compiler available. And this is
the NVIDIA one, right?
This is the NVIDIA compiler. So this is super interesting. So obviously we're not actually using any GPUs as part of this event, but the NVIDIA compiler, or it was born out of the PGI compiler.
Yeah, it's got a long history in HPC, hasn't it?
Really strong history in HPC, and is LLVM based, and has a really strong Fortran compiler. So for those people that are interested playing with that, or might be interested in some of the Grace systems coming up from NVIDIA in the future, this is a really good opportunity to have a play with their compiler suite on an ARM system.
And you make a good point there, something that we want everybody to understand. You know, we're doing this, we're running this hackathon this summer on AWS Graviton 2s, you know, in our AWS cloud. But we're trying to lift the tide for all of the boats in the ARM HPC world. So regardless of what platform you end up on, we really, you know, this is a community effort across all of the folks that are using ARM for HPC.
And this event is being driven by the ARM HPC users group. So this is as friendly as we can get it. It is a hug.
Yep. Yeah, it is a hug.
Got to get that pun in there.
That's nice.
Right. So the application that we're going to be using is going to be Cloverleaf. It's nice and quick and easy. So I can have a look at what Cloverleaf actually needs. And this kind of gives us an idea of also why we need Spack. So, apologies. So I'm just going to ask Spack, what does it need to build a version of Cloverleaf using the ARM compiler? Now, that's a pretty damn long list. And most of this is the dependency chain caused by OpenMPI, right? We're building an OpenMPI as part of it, and we have variants in here. A lot of these are AWS specific, so we're building with the OFI fabric to get the EFA support, building with PMI support, we're using Slam scheduler. So all of these things are configured to the system that we're running on. And this is why Spack is needed, because all of these things need to be built. Now, as it happens, I've pre-built all of these, so I can go ahead and just install this. And this will take about 20 seconds. It will go and validate that all of these things are installed. Go and pick out Cloverleaf, build it, install it. And again, for a small code like Cloverleaf, this really doesn't take long. And again, it's worth noting that we're running these builds on a 64-core head node, so actually we're throwing quite a lot of parallelism at these. So this is fantastic. So I'm just going to do the same for GCC and wait another 20 seconds. And then when it's done, I'll do the same for NV HPC. And this will give us a single application with all of the same build configurations installed with 3 different compilers. And what's important here with Spack is not just the application it's built with 3 different compilers, the whole dependency stack is built with the different compilers. So
great.
MPI is installed with NVHPC. Perl is installed with NVHPC to support that. So everything is correct for the application that you're installing, and Spack manages all of that for us. And that's just so useful.
Right.
So that's now finished. We can just do a quick check. LV. Great, so we've got all of our different versions of Cloverleaf installed. Now, that was trivial because we know that the Cloverleaf application works. In reality, when you're picking up a real application, this is going to be much more difficult. But now gets into the kind of really interesting side of things. So we've already checked out our Git repo, and inside of this folder is 2 test cases that I've pre-prepared for reFrame. So if I bring up the smaller of these, bear with me. Excellent. So this just describes that we're running a benchmark. We're running it on the C6G nodes because at this case, we're just doing single node runs. We're defining the benchmark that we're running, the application executable, where the output files are being generated. And then we talk about which compilers and application that we're using to run with. Now, I've just installed Cloverleaf for all of these 3 compilers, so that's perfectly valid. And then we can do a load of MPI runs. Now,
this is the brilliant part of reFrame.
Absolutely.
Go do all of these runs for me.
And it just does a state space expansion and says, right, for every node type, for every compiler instance that you've given, for every MPI count that you've said, go off and generate the job, and I'll generate you your Slurm script that does that, and I'll submit it, and I'll analyze the results when they come back in. So this is like super valuable for us. So I'm just going to run it on 2 MPI types just to keep things simple. Right. And it's important to just mention the validation side of things here, because we're not just looking for fast runs, we want correct runs. So I've written this Cloverleaf demo file to look for specific values of kinetic energy. I generate lower and upper thresholds for that validation phase so that we know that we're right. There might be a bit of arithmetic tolerance issue there, that we want a little bit of threshold in there, but we want to know that we're getting the right answer. But I also want to know how long it takes. So we have some regular expressions to extract performance data from that. So this is the important side of reFrame. And I'll let you browse all of these on the GitHub repo at your own leisure. But this is all we need to do.
You know, the thing for all of the participants in the hackathon is, you know, we're providing all this stuff in a GitHub repo. These are templates. You can steal this code and just like repurpose it to your code straight away, so that you don't have to do a PhD in reFrame to understand how to get all this stuff going. You can just copy our templates, right?
Yeah, exactly. So what I'm going to do is just pass that all to reFrame and say, you know what, run that configuration file. And what you'll see reFrame doing is that state space expansion. So we've got 1 node type, we've got 2 different MPI counts, and we've got 3 different compilers. So there should be 6 jobs generated as part of that. reFrames staged all of those into their own directories, generated the Slurm submission scripts that load the right compiler, load the input files, know how to generate the output file, and start kind of bringing all of that data together. Now, if this has worked, we should start getting some results back pretty quickly. I can do a...
Okay, so a couple of minutes have passed and we've watched all our jobs run. Let's have a look. What's next?
Yeah, so reFrame's come back and said, well, it's gone off and run all of these jobs, and of the 6 combinations, it's validated all 6 of them, so it considers the test to be passed, which is great. One of the parameters that we passed to reFrame was performance report, and it just generates this nice little ASCII performance report at the end of our run that says, well, you know what, this is how long each of your different configurations took to run. So if we just pick the top 2, right, we're running Cloverleaf with GCC, and we're running on 32 MPI processes and 64 MPI processes. So this is half a node and a full node, and we can see that the time taken drops from 34 seconds to just under 18 seconds. So that's, yeah, it's pretty good scaling in this sense.
That's actually, no, that's great.
We're really happy with that. And similar behavior for the ARM compiler. NVIDIA compiler doing something interesting. And this is the kind of thing that we're going to want teams to look into. So it's actually got identical performance of both 32 cores and 64 cores.
Wow.
What's actually most likely is that it's been able to use some OpenMP threading that we haven't explicitly disabled, and is actually using the full resource for this test case anyway. But This is the kind of thing that we want teams to actually start questioning results and go, hey, that's not apples to apples. Like, we shouldn't be getting 2x faster in this case. So why is that happening? What's causing that? Or is it just that the compiler's magic and is doing some really good job there, and and this is the right compiler to be using for it? So this is kind of really representative of what the students are going to have to go through.
Now, during the event, we're also going to have another base reference for people to compare to, like another baseline to compare to, which is x86 instances with all of the same environment built on them. So the folks, where you can do all of the same Spack commands to build the same package. In most cases, we know that these packages build really well on x86 because, like everybody understands, it's what we've all been doing for the last 25 years. It's a known target, and we'll be able to compare the scaling curves. If you're running these things across 1, 2, 4, and 8 nodes to see how codes scale, you should expect to see roughly the same shape scaling curve across both CPU architectures. And if it isn't, it tells you something. And it might tell you got something wrong in the build environment, something wrong in the run environment, or it could be something deeply indicative of how the code works. And like I say, any of those things, we want to know about all that stuff, and we want to unearth it so the community can address these things.
Absolutely, and that's a perfect segue onto the next section. So when we're talking about performance curves, one of the ideas that we have behind this is, well, rather than you just generating this performance data, let us capture it. So what we've done is set up a logging server that ingests all of the performance logs and data logs that are coming out of reFrame and stores those in our log server. So I've just refreshed it, and we can see the performance report that reFrame generated for our application. And so I can see all of these performance points inside our log frame, inside our log server from reFrame.
From reFrame, yeah.
Now, what's really interesting is if we actually dive into some of the individual elements, we can see the Spack environment that was used to run the benchmark that we were running, the application, how many cores it was being run on, how long it took to run, all of this metadata surrounding the run that we can start to build queries and visualizations around. So this is kind of one of the things that we've been playing with behind the scenes, is actually, well, right, can we start creating scaling curves and visualizations and demos based on the ingested log data? So this is just an example of what I've got set up querying for the Cloverleaf test case at the moment. I've got it set up for our BM16 test case and our BM512 test case, and it's just starting to pull in all of these different data points from our multiple compilers running, in this case, single node, and pulling in, well, right, what performance are we getting, and what is our best performance, so that we can start doing performance regressions over time. We'll be using this as a slightly competitive aspect to this. So being able for us as organizers to see which teams are on track and who's doing the best in terms of number of applications ported, test cases working, compilers used.
All of those things are worth points, right? In our sort of
absolutely
point system. Yeah,
absolutely. We've devised quite a complex point scoring system that means that teams will be rewarded for basically anything that they do that is helpful. It's not right. You've got to take this one big monolithic application and all 4 team members have to spend a week down in the weeds putting I don't know, vector intrinsics into the code to get any points. If that's what you want to do, great, we'll happily accept that. But also if you just want to start building lots of different codes, working with different compilers, building different test cases, different MPI variants, doing network studies between the C6G and C6GN instances, like all of this work has associated points behind it that we'll be using to reward teams for their effort. And Booth is right when it says, like, we really are just rewarding the team that moves the needle the most. There's been a lot of discussion about, well, what codes are we going to use? So we've tried to keep this a bit secretive, and we'll be publishing it later in the week. But basically, we've got a list of about 100 applications that we're going to make available to students, and these already exist in Spack. So you're not going to have to be going out and writing Spack recipes from scratch. This is all existing, but in many cases we just don't know if it works on ARM, and certainly don't know if it works across 3 different compilers and different MPI variants and all of that. So,
and we certainly don't know necessarily whether these codes work and give validated, valid, correct answers.
Right, and that really is the most important factor.
Look, the highest level goal that we've got here is to improve the performance of all these HPC codes across all of the ARM-based CPUs that are out there in the world. The only way that we can get better performance is if we know what the current performance is, and we also, and to work out that performance baseline, we've got to get them to build first. And in some cases, it's that build part which could be the biggest, contribution that a team makes. There may be a team out there that's going to do nothing but fix build scripts across the board and get things building. That could actually win them the prize.
Absolutely.
Right.
Absolutely.
So, or there could be a team out there that's just going to move the needle for a single code and do a Herculean effort. We just don't know yet. Hey, Olly, thanks for coming along and explaining all of this.
Always happy to.
We're going to keep putting more details up on this page. If you want to find where to register, go here. If you want to find more details, go here. Bye.